Hello, everyone. So thanks for introducing me and Tadas. It's an honor because at least I don't have to lie from the beginning. So if you see us lying, so just raise your hand and don't hesitate to ask questions at any time of our talk. And I'm really happy to be here at Agile conference. And basically, I want to talk about one Agile technique that you can put to Agile to your Agile tool belt, which is called mutation testing. And mutation testing is a technique to assess your test code quality. So who knows what mutation testing is? Oh, cool. So at least...
And raise your hands again if you have used it on a project.
Okay, cool.
No?
So at least we have a great audience to introduce the tool and talk a little bit about our experience. So, and please ask questions anytime. Just interrupt us. Don't hesitate. And before we go into serious stuff, let's talk about more interesting, entertaining stuff. So today we're going to talk a little bit about music, but not really about music, more about bands, about rock stars, and in particular one band which is called Van Halen. I'm not sure if you know it. I'm not also a big fan of them, but they are famous for one thing, which is their Band Tour Rider. And let's introduce what is Band Tour Rider. Band Tour Rider is a contract between tour organizer and the band. So if you want some particular band to go and play at your place, at your venue, you have to fulfill all the requirements in Band Tour Rider. So some band tour riders are really thick. They are big books of requirements, and it's sometimes really tedious and hard to fulfill all of them. So, for example, Britney Spears wants to have Princess Diana framed photo all the time. So she has such a requirement. So she's quite a pretentious one. For example, Katy Perry wants to force all the drivers that she's going to be brought to the hotel, not to stare at the rear view mirror, not to talk to her. So this is a requirement. She wants some kind of privacy. And some bands actually understood that this is quite a pretentious from some to be a rock star, and they put something like this. This is Foo Fighters' hilarious tour rider, which contains a section with some activity pages. So for example, you have to circle items that belong into the salad. So this way they're actually asking you to be involved more into fulfilling requirements, not by just reading them and doing real stuff, but also doing some gamification. And for example, our people are vegetarians, so they ask not to sell any meat during the concert. And let's go back to Van Halen, and let's talk about famous Van Halen tour rider, which comes from 1982, and that tour rider has one interesting line in it. It says that, okay, you have to provide M&Ms, but absolutely no brown ones. So sounds really pretentious, right? But there is a story behind this. The story is that at that time, Van Halen was a really big rock star band, and their shows were really containing a lot of equipment, a lot of stuff to put on the stage. And there was an accident that some organizer didn't read and didn't pay a lot of attention to their tour rider, and the whole stage sank down, almost killing the tour technician. So at that point, they were thinking, what to do? So they added this line, and if they find any brown one M&M in their jars in the room, they think, okay, there's something suspicious. They probably didn't read carefully all the requirements. And if that happens, they are allowed to stop and not perform at the audience, or at least they have to go and check if their equipment is perfectly tuned. So this is a good example and illustration of today's talk, how to add small thing, small detail, which actually verifies all the big stuff. So if one thing fails, you know that something is not right. So we're going now to be more serious, and let's talk about our agenda.
Yeah, so the things that we're talking about today is divided by 3 parts. The first is just test quality and code coverage. Then we'll get into mutation testing in theory, and then we'll see some practical examples. So let's just dive into it. So production versus test code quality. And here, when we say production code, we refer to like your library code or your application code or something like that. So, and the test code obviously is the code that tests that library code. So we all know that code has bugs, right? Like we've all seen them, we all fight them every day, and we want to have as few of them as possible, right? And and thing is that tests are also code. So therefore, tests have bugs too, right? And now for your production code, you usually write tests, so you know you know that your code does what you expect it to do. So how do you who writes tests for your tests?
And there is one important thing, that we assume that test code is the same, it has the same importance as your production code. That's our axiom that we are following today. So we're not discussing this anymore. So who watches The Watchmen? And when we talk about test quality, we usually mean readability. For example, your test has to be readable. So that's the quality code. If you can quickly understand what's going on in your test, it's readable. It should be focused. It has to do one thing and do it right. It must be concise. It should be simple, short. You should quickly find in few lines what the test is doing, what is the requirement that the test is trying to assert. And it has to be well named, so it has to communicate what the test is doing by having the good names which explain the test's workflow. So the program testing can be used to show the presence of bugs, but never to show their absence. This is an important statement, that we never are sure if we caught all the bugs in our source code.
Right, so let's look at some of the metrics that we can assess. So the first thing we want to talk about is code coverage. And what code coverage is, actually, how many of you know what code coverage is? Okay, almost everyone. And does anyone have a requirement at work, like to have like some certain level of code coverage? Okay, a few people. So that's interesting. And
who uses code coverage daily? Like just reads the report or has it in your CI? Cool.
Okay, so for the ones that don't know, code coverage basically just tells you how well your source code is covered by tests. So you basically the one thing, the most important thing is you get this one number that tells you, let's say 80%. That means that 80% of your source code has been executed during your tests. So there are different types of code coverage. Probably the simplest one is the line coverage. People say often, well, we have 100% coverage. They, quite often refer to the line coverage. Then there's branch coverage, which is a bit more in-depth coverage, and there are plenty more, but we're not going to get into them today. But so basically when you run your tool, you see something like this if you open like one particular file in your report. So here, the green lines represent like the code that has been touched during your tests, that has been executed. The red ones have not been touched, and the white ones are irrelevant. So you can see some code comments or just some syntax or empty lines, just irrelevant stuff.
An important detail is that you should see how much code is not covered by your tests. So this is indication that you're not doing anything in your test with that part of the code.
Right. So, okay. So let's look at an example of line coverage. So let's say we have a method like this. We have some pseudocode here. So it's just a method that returns a string, adds A and B. We have an assertion for that, and basically here we have full coverage of this test. Now if we have a slightly more complex example where the return value depends on the argument that you pass into this method. Here we have this ternary operator, and for those unfamiliar, it's like just an if condition. So if you pass true to it, it will return A, otherwise B. And yeah, so here if we have the same kind of test that will just one assertion. In line coverage, this would mean that you're 100% line covered. But in reality, you see like this B string could be just, like a super complex method that does a lot of things. And so this just illustrates that you can't really, that line coverage is something that you can't really be sure that, everything is executed. So that's where branch coverage comes in, which makes sure that you get into every branch of your source code. So in this case, you would need those two assertions to have 100% coverage.
So basically, the idea is that you need to have two tests that actually examine both both possible outputs from this line. So it's not enough to have one single assertion.
So yay, 100% code coverage. As you can see, it's so it's a useful metric to have. It's something that doesn't really tell you that your code does what you want it to do or what it's supposed to do, but it's at least you know that everything has been touched. So can you trust 100% code coverage? So obviously, as you've seen by the previous image, you can probably guess that you can't really trust it, or if you really tried it. Because mainly code coverage can only tell you what is not tested. So the red lines are very the key things that you want to pay attention to. You know that the stuff has not been executed, and the green lines, it might be correct, might not be correct, but at least you know that those are executed. So that's useful already.
And if you're not using language like Java, for example, which is compiled language, you may end up in such situation that you write a code, you execute it in runtime, and you find out that your syntax was incorrect. So having 100% of code coverage at least means some similar thing like full compilation for your dynamic language.
Right. So, and one other problem with code coverage is that it can be gamed. So for those of you who have this requirement at work to have some certain code coverage, you can obviously simply have call your methods in your tests, and that will have if you call all of the methods basically with all the different parameters, it will probably have good code coverage, but that you can have like 0 assertions.
Yeah, you just may on purpose omit any assertions, and you still have a test, which is called test, but it's not a test. It's just like examining of your code without asserting the output. So you can game the coverage.
Right. It can also be gamed by accident, actually. So you might think you're asserting the thing that you want the behavior to be, but it might be.
For example, you just can forget to put assertion. You just spend a lot of time preparing for the test. You wrote you wrote something which like exercises your system, and then someone called you and you just forgot to add assertion phase, and you see that okay, I have full coverage, and let's move to another feature.
Or it might just be asserting a different thing than you think. So that's where mutation testing comes in.
Yeah, and let's talk about mutation testing. So mutation testing is, as we saw from the example from Van Halen, it basically means that you add something what you don't expect to the soup. So, for example, in mutation testing, we try to introduce a bug, and we need to see our tests failing. If they don't fail, it means there is something wrong with our tests. Don't forget that today we're talking not about production code quality, but we're talking about your test code quality. So mutation testing, what it does, it changes your program code and expects your test to fail. Usually when we talk about mutation testing, we mean some automated tool. So if we just talk about all those concepts, we mean that those concepts were implemented in some tool, either for Java, for Ruby, or some other language. So what exactly is mutation? What type of mutations can be? If we talk about regular refactorings, refactoring is not a mutation. It's just equivalent transformation of your code to some maybe better or worse situation. But when we talk about mutations, we talk about some simple changes. For example, your method might always return null when you expect it to return some real value, or it may always return true, or you can change operator to some opposite one, or introduce arithmetic operator changes. So mutation is simple. It's simple bug inserted into your program, and there are a big list of those possible mutations.
So yeah, so let's look at some terminology, how we call things in this mutation testing world. So when we apply a mutation to this piece of code that we take, that we call this new piece of code a mutant. So you know, in the previous example, like these ones on the right would be mutants, and then we after we do this mutation, we run our test suite. Now if all of our tests pass, then we say that the mutant has survived. And if the test fails, or any test fails, we say that the mutant has been killed. So basically, you know, mutants are bad. You want them all dead. And yeah, so it might be slightly counterintuitive in the beginning because you want your test failing. But yeah, so now failing is the new passing.
And I want to illustrate how mutation testing can be really useful. We're all human and we make mistakes. So this is a classical example about mutation testing when we use test-driven development. And well, if you do test-driven development properly, you will never end up with the bad test suite, right? But in this case, let's look at simple thing. We will try to implement a function which is max, and obviously it should find the largest number in the array. Array can be arbitrary length, and let's try to implement it using TDD. So first we start with a failing test, and this test will accept an array of single element, and that element is 0. So maximum value of that array is 0, right? So implementation is as simple as this. You just return 0, right? Now we have one passing test, and we start writing another test, and that test is like find a maximum of another one single element array, and this time we cannot go with such implementation, so we need to modify it a little bit. So what we do, we just return the first element. Okay, we move on and we try to increase the size of array, which is natural, and eventually we come up with such a solution. And I feel that this solution it should be okay. It should work with all the arrays, right? And our code coverage is 100%, right? So is there a problem? So we should probably run a mutation testing tool and see what happens. And our mutation testing tool does really simple thing. It replaces condition to true. And guess what? All those tests pass. So there is a simple problem that we forgot to follow this driven development practice, which is called do it in baby steps. And instead of writing a lot of code, we should see what is the minimum amount of code that we need to write to pass the test. And in this case, it was like just simply return all the time the last element. So what we do, we write another test, which is now failing, and now we get to our previous implementation. So what mutation testing did for us, it has shown that we are missing a really important test in our code. So which means that if later I would be refactoring this code, I would come up with something what is invalid implementation in this case. So baby steps matter.
Right. So your test effectiveness is measured by the number of killed mutants by your test suite. In other words, like you have all of these different versions of your code generated by this tool, and now basically, if your test suite kills most of them, you say that your test suite is pretty effective. Yeah. So it's in a way you can say it's like hiring a white hat hacker that breaks into your server and makes sure you detect it. Yeah. So what do we do if the mutant survives? There are different ways you can solve it. So the first thing you can do is just simplify your code. So let's say if in the previous example, what we had in our tests, if that were the requirements, actually maybe we didn't even need to do that if condition there, right? Like if all the tests pass with that, then it's probably good enough, right? But yeah, so or another thing would be to add additional tests, which is what we actually needed in this previous example. Yeah, and like in general, if you do TDD like by the book, the way it's meant to be, minimal amount of code to make the test pass, that will usually you will usually have a pretty good mutation coverage. Right. So what are the main challenges for mutation testing? Why is it not so popular? Why so few people raise their hands today? I guess one of the things is that it's pretty slow. The computation cost, because, well, you can imagine if you have a large code base, you need to get and there are all sorts of different ways you can modify your code, right? You can change anything basically, right? And so you generate all of these different versions, and you have to run your test suite again, the whole suite for your for every mutation. So that takes a long time. So yeah, so the second challenge would be that sometimes you get equivalent mutations. And so basically you get two versions of your code, but in your case that means the same thing. And we'll see some examples next up. And the third problem is infinite loops, which, yeah, sometimes the code or like stuff like when the mutated code is just not really valid running, you know, like you have a, yeah, well, we will see an example actually. So yeah, so an example of an equivalent mutation would be like right here. So on the left you see the original code, which has a while loop in there, and there's this not equals sign, and if it was mutated to a less than, you know, in this loop when you're just incrementing a number, that means the same thing, right? Like it makes no difference for your code, right? So it's not a problem really. But yeah, so the tip here would be that like usually if you try to use just a stricter version of the operator, that will usually well, depending on the tool, but most tools are smart enough to not generate mutation to a less strict operator, because that would obviously make your test still pass.
Okay, and now let's talk about infinite runtime. So what happens? You have an expression which well, evaluates, and you do something until this expression shows that you need to terminate. And in this case, if mutant changes that expression to true, it becomes an infinite runtime. So the solution to this problem is to introduce timeouts. So basically, that's how all the tooling deals with that. If something runs too long, you have to have a timeout for such test. And idea here is that usually mutation testing tools are used only with unit tests. So you don't do that with integration or end-to-end testing, where tests might take like quite significant time to run. So disadvantages.
Okay, so the disadvantages are, yeah, again, that it can be slow, and it's sometimes hard to just run it as your everyday TDD rhythm. And it can also be very noisy. So again, if the code base is quite big, you'll get a lot of different mutations if you haven't used such a tool before, or
So the idea is that if you just introduce mutation testing tool in your big project, you probably didn't follow all the best practices that mutation tool is going to force you. So you will get a lot of warnings about your stuff that it simply says, for example, a lot of equivalent mutations or something that you will probably not have enough time to fix quickly. So this is sometimes a disadvantage when you introduce a tool. So let's talk about one thing. Is it really slow? Like, disadvantage is that you probably could not use it for test-driven development, but let's look, is it really that bad? So let's say that we have a big project. Well, big in this case will be just 300 classes. And we have around 10 tests per class, and let's assume that one test runs around 1 millisecond. So in total, we have a test suite which runs, finishes in about 3 seconds. So not that bad, right? Really agile stuff. Probably your unit tests are written in a really good way. Now let's add some mutations. And let's assume that we will add 10 mutations per class. Usually this is also configuration parameter for your tool. For example, you can say that don't mutate this source file, for example, more than 10 times. Because there should be some kind of limit. It's really easy to produce a lot of mutations. So what happens now that we have 3,000 mutations, so it's for 300 classes, we have 10 mutations, and runtime with all the mutations now is, well, it's like, because for each mutation we have to run a test suite, right? Now it's 150 minutes. Well, it's definitely not acceptable, at least if you do TDD and you want to get a quick feedback. Maybe for like some continuous integration server, maybe it would be acceptable, but not definitely for daily work. And let's assume, like the question was like, you should probably also include the compilation time. Let's assume that it is quite quick, because if our test runtime took like 3 seconds, so let's assume that it includes compiling as well. So,
or maybe we're not using a compiled language, but yeah.
Just easier. Okay, so let's speed it up. So the problem is that we're running maybe too many tests which are not important to the mutation that you have done. So idea is that I'm doing mutation in some particular class, and if it is unit test, it probably doesn't have to do anything with our class which has their own unit tests. So the idea is that you should run only those tests that are covered by code coverage tool and which mutation tool was running before. So mutation tool usually knows that, okay, this place is covered by the test, or this place is not covered at all by the test. So you don't need to run mutations that are not covered by tests. So in this case, we can speed it up a little bit. So if we have 300 classes, we have 10 tests per class, and we introduce 10 mutations for each class, and we have 1 millisecond test runtime. So our total mutation runtime shortens up only to 30 seconds. So it's like 10 tests, 10 mutations, 1 millisecond, and 300 classes. So it's quite a big improvement, right? From 150 minutes to 30 seconds. So if you put such heuristic to your tool, it becomes useful, but still it is not that useful, right? You don't want to just make a simple change and wait for 30 seconds to see is it like green or red, right? So what you should do later, you should cover only, like run tests only that cover your current changes. So you can run like a full test suite which runs 3 seconds, then do mutation testing, which only deals with the current changes that you have done to your source code. So this way you have a really quick response time, and you can use it in your TDD lifecycle. So that's not that bad if you're smart to use the tool. Yeah, and all those tools actually have some configuration options. You can, for example, if you use Java, you can have a Maven command to do this thing.
So let's look at some usage scenarios. So the first one would be, like Vaidas has mentioned already, like you can just hook it up into your CI and have it run there, so you don't have to wait for it every time. Just when you push it to your CI server, Jenkins or whatever you're using, and yeah, then you can just see it there. Another way would be you can do like in your day-to-day TDD rhythm, but only looking at mutations for the code that you have changed. So there are also tools that look into your Git diff or other source version managers. Yeah, and the third one would be like, so yeah, if you have a legacy code base that is very long and you have like too many failing mutations and too many alive mutants, then you can only also produce a warning report out of it. So you don't have to make your build fail because of that, but you can still examine all of the cases.
And the whole point is that you shouldn't hold yourself from using the tool just because you have like someone says that, okay, this is legacy code and we cannot just add a tool which starts to break and it's like a big change. No, just add the report. Maybe someday you will see that, okay, if I write a new code, that report can increase the quality. So just learn about the tool first, and that would be a big advantage into using this kind of tool.
Okay, so let's look at some tools. Just naming some examples. So if you use Ruby, there's Mutant, which is pretty good. For Java, there's Pit, which is probably the most advanced mutation testing tool that we know of. And yeah, there are for other languages many, but yeah, you can come to us later if you want to. So yeah, so let's get into the summary. So basically, code coverage just highlights code that definitely is not tested, so mutation testing highlights code that definitely is tested, so it's quite like the opposite thing that you get out of it in comparison with code coverage. And yeah, that's your favorite one.
Yeah, and that's my favorite one, which says that if you introduce some bug into your code, your test should fail. So mutation testing with a good test suite should work as a hash function for your test code. So if you introduce bug, it has like two-side network connection, and if something is wrong on one side, on our side should indicate that. Okay, so time to talk a little bit about us. So my name is Vaidas, and I really want to thank my company which helped me to get here, Wix.com. I'm working there. So thanks for my company, and if you want to contact me, you can do it on Twitter, or just Google me, or just come and talk after this talk.
Yeah, and I'm Tadas. I'm primarily a Ruby programmer, but yeah, thank you. And we want to thank to the people that inspired us the most to do this. It's Marcus Scherp, the author of Mutant, Henry Coles, the author of Pit, and Philip Van Lin, who's writing a book about mutation testing, and we took a lot of inspiration and some quotes from there. And Van Halen, of course. Yeah. So yeah, any questions?
I think the answer is yes, because well, I think the answer is yes, because I just this morning watched Pitt's author's interview, and he said that he has a plugin for that. So you can integrate in this tool. It works with Maven, with Gradle, and it should work with SonarQube. I haven't tried this myself, so. Yes, please.
So, as I understood, you are using mutation testing in every day's developer's life. So, could you just shortly maybe summarize how this applying mutation testing helped you, like, I don't know, improve tests in general? What were the most, I don't know, in general, how the test quality improved and so on?
So I think for me, like I've found a lot of missing tests that sometimes, you know, sometimes I also do get lazy and skip some baby steps and then don't write the tests for the code and you know, just write more bigger parts of the implementation in a way, and then that lets me catch that. And I mean, thing is, like, it's kind of hard to say if it you know, if because of that, like, I feel that because of that we have less bugs and higher quality software. But yeah, I haven't actually scientifically measured that. So
I think the problem is that when you're like into those tools, into best practices, it's really hard sometimes to find the bug. But if you add additional tools, definitely you get more relaxed because those tools report really quickly that you're doing something wrong. My experience with Java and mutation testing tools is that I was never thinking about some IDE generated code. For example, I just generate toString method and usually just forget to properly test it. And this tool, after I saw a report, I saw so many interesting things there that now I'm a bit more cautious by generating the source code. So that's my take from this.
And also, again, to answer the question of our title of the talk, I think like for me personally, it helps trust my tests better. So because of that, I use the tool and I can deploy more confidently without worrying. Does that answer your question? Sorry? Yeah, so we try to keep it over like 80% at least.
And I think the goal is that, for example, with code coverage, definitely you want to have 100% code coverage. It's really easy to achieve that, and really easy to have not quality achievement with code coverage, but to achieve 100% of mutation coverage is really hard. I mean, if you're writing something and you're a bit slacking somewhere, this tool is going definitely to show this. And sometimes it changes the style that you're writing. For example, if you have equivalent mutation, you start to think, okay, maybe this operator is not the best here. You can use something which actually does what you want. And it changes the way you think. And you start to spot those locations of the. You start to think a bit like a tool sometimes. This is probably not very good, but you sometimes start to spot the patterns. I have a really quick answer. We talk only about unit tests, and if you write proper unit tests, you don't deal with like third-party API, you just mock it. So, well, you only have your own code which is being mutated. So you don't have to deal with such issues. It doesn't make sense. Like, you cannot do anything about. Well, probably you could report something to the provider, but it's not for them. It's for us.
Because you try to improve your own test quality, right? So.